Some objects are too small to see, so we invented microscopes. But some objects are too small for microscopes to see, so we invented electron microscopes. But then there are objects that are even smaller, and in our everyday world, they rarely actually exist. These particles need high energy situations to pop up. Those high energy situations are generated by particle colliders. Particle colliders are huge complexes used to observe tiny things. The Large Hadron Collider has a circumference of 16.6 miles. Along this length of track, particles are accelerated in a vacuum using powerful electromagnets and electric fields. These magnets and electric fields are made stronger and more compact by superconductors. Superconductors must be very cold to work, so they use liquid helium to cool off to a temperature a few degrees above absolute zero. The particles in the accelerator are sped up to nearly light speed, moving in opposite directions. Once they are moving fast enough, they are made to collide. Imagine the energy in a head-on car crash. Two cars moving toward each other at 60 or 70 miles per hour. Now imagine this same situation at a significant fraction of light speed. The energy in that collision would be so immense that it would generate a huge explosion for miles or hundreds of miles around. On the scale of single particles, the explosion isn't as disastrous, but it's still enough energy to generate interesting and new particles like the debris from this hypothetical car crash. Out of all the matter particles in the Standard Model, only up quarks, down quarks, and electrons are common in everyday life. Up quarks and down quarks make up protons and neutrons, and combined with electrons, they make up atoms. But where do the other particles fit in? The up quark, down quark, and electron all have two higher mass cousins, each that rarely exist in the universe. There is also a whole set of very light, neutrally charged particles called neutrinos that rarely interact with other particles. Take the muon, a higher mass cousin of the electron. Muons are unstable and have a half-life of 2.2 microseconds. They don't stick around very long. When they decay, they release a negative W boson and become a muon neutrino. Then the negative W boson decays into an electron and an anti-electron neutrino. Despite its short half-life, the muon is actually the longest-lived of the unstable particles in the Standard Model. All of the other ones decay into up quarks, electrons, and neutrinos, as well as their antimatter equivalents, in a fraction of the time that they do. The use of particle colliders to see these different particles is that when we collide two particles at near light speed, the energy generated is enough to create some of these high-energy, high-mass particles. Unfortunately, these high-mass particles often decay before they can be picked up by the detectors. Fortunately, the decay products act like the shadow of the original particle and evidence its presence by showing up in the detector. Through a close analysis of collected data, the original particle can be deduced from its shadow. That is how the Large Hadron Collider found the Higgs boson in 2012. Particle colliders reveal exotic particles that could only exist in the most extreme conditions in the universe, like the Big Bang. Learning about these particles gives us a fuller sense of reality, and may reveal how things worked in the distant past. The larger a collider can get, the more energetic collisions it can make, and the more particles it can reveal.